Have you ever stopped to think about what a simple spinning top and the moon have in common? It's actually a lot more than you might think. Today, we're going to pull back the curtain on the invisible laws of physics that connect the tiniest little movements to the most massive forces in our universe. So let's dive right in. Yeah, it sounds like a bit of a riddle, doesn't it? But the answer is a really fundamental law of physics, one that pretty much affects, well, everything. So keep that question in the back of your mind, because we're about to jump into our first big idea. All right, so let's start with something super familiar, something we've all seen a million times, an object just moving in a circle. On the surface, it looks pretty simple, right? But the physics going on behind that spin, oh, it's way deeper than you'd expect. Okay, so in physics, this has a name, uniform circular motion, or UCM for short. Now, here's where it gets a little counterintuitive. Even if the object's speed stays exactly the same, picture a car going a steady 30 miles per hour around a bend. Its direction is constantly changing. And get this, in the world of physics, any change in direction, even if your speed doesn't budge, is technically acceleration. So if it's accelerating, something must be causing that, right? Well, the secret ingredient here is something called centripetal force. The name actually means center seeking, which is a perfect description. It's this constant inward pull that keeps an object from just shooting off in a straight line. It's the force that's constantly yanking it back and keeping it on that circular track. And once you start looking for it, you see this principle absolutely everywhere. If you're swinging a stone on a string, the centripetal force is the tension in that string. When a car makes a turn, it's the friction between the tires and the road that's pulling it in. And a satellite orbiting the Earth, well, what's the force there? That's exactly where we're going next. This is where things get really cool. How do we make the leap from a simple toy on a string all the way out to the stars? Well, let's connect the dots between that little swinging stone and the orbit of our very own moon. Just look at this side by side. On one side, you've got the stone on a string. That inward center-seeking force is the tension. Easy enough. But on the other side, you've got the moon orbiting the Earth. So what's the invisible string holding it in place? What's the force pulling the moon inward, stopping it from just flying off into the void? It's gravity. It's the exact same principle, just blown up to an astronomical scale. Incredible, right? And that was the stroke of genius from Newton. He realized that the very same force that pulls an apple from a tree to the ground is the one acting like a giant cosmic string for the planets. So let's go back to our original question. What does a satellite and a car on a roundabout have in common? They are both being held in their circular path by a center-seeking force. For the satellite, it's gravity. For the car, it's friction. Okay, so we've got a handle on the forces. Now let's talk about what these forces actually do. And this brings us to a concept in physics called work. And I'll tell you right now, it's probably not what you think it is when you hear that word. See, in physics, work has a very specific, very strict definition. You are only doing work on an object if you apply a force to it and that force causes it to move some distance. If it doesn't budge, it doesn't matter how much you're sweating or how hard you're pushing. In the eyes of physics, you've done zero work. Nothing. This little chart here breaks it down perfectly. Think about lifting a box off the floor. You apply a force up, and the box moves up. Force and motion are in the same direction. That's positive work. But what about just holding that heavy box perfectly still? Your muscles might feel like they're on fire, but because there's no movement, you're doing absolutely zero work. And then there's friction. Since friction always pushes in the opposite direction of motion, we say it does negative work. It's basically trying to steal energy away from the system. So this ability to do work, that brings us to maybe the most fundamental concept in all of science, energy. Seriously, you can think of it like the currency of the universe. It's what gets paid to make anything and everything happen. Now, for what we're talking about today, energy basically comes in two main flavors. First, you've got kinetic energy. That's the energy of motion. If something's moving, it has kinetic energy. Simple. Then you have potential energy. That's stored energy. It's energy that's just waiting, ready to be unleashed because of an object's position or its state. And this all leads us to what is, without a doubt, one of the most powerful and unbreakable rules in the entire known universe, the law of conservation of energy. It's the golden rule. It says that the total amount of energy in a system can never be created or destroyed. Ever. It can only change its shape, transforming from one form to another. The absolute best way to picture this is with a roller coaster.
Imagine you're at the very, very top of that first huge hill. You're barely moving, just kind of hanging there. At that moment, you are packed with the maximum amount of stored potential energy. Then you start to plummet. All that stored potential energy is instantly being converted into the energy of motion, kinetic energy. By the time you hit the very bottom, you're going as fast as you're going to go with maximum kinetic energy. But here's the key. The total amount of energy, potential plus kinetic, stays the same for the entire ride.
Okay, so this isn't just about fun physics lessons and roller coasters. This fundamental law that energy just changes form is literally at the heart of how we power our entire world. It explains, well, everything. When you look at our energy sources, they pretty much fall into two main buckets. You've got your renewables, things like solar, wind, and hydropower, which, as the name suggests, get naturally replenished. And then you have the non-renewables, like coal, oil, and natural gas. We only have a limited amount of that stuff. And here's the big connection where it all comes back together. Every single energy source we use, I don't care if it's a lump of coal or a high-tech solar panel, is simply a different method of transforming energy from one form to another. When you burn fuel, you're converting stored chemical energy into heat. A wind turbine? That's just converting the kinetic energy of the moving air into electricity. It's all the same fundamental law, just in different packages. So, in the end, the laws of physics hand us the blueprint. They show us how energy works and all the ways it can be transformed. The physics gives us the tools, but the real question, the one that matters for our future, is how we choose to use those tools. Which sources we decide to rely on, and how smartly we use them. That's not just a question for scientists anymore. That's a question for every single one of us.